chose to do that for us. It is on you.
Okay.
Thanks, Rob.
Once everybody's settled, I'll
Very
start
for
the
your
talk.
support.
I like your hand pump cover.
You could use this to get
I mean, true. Fair enough. Fair enough.
Okay.
All right, welcome to the Angr talk. This talk is authored by Tristan, who is not me. I'm Daniel. Tristan is mega sick, he said. So he's doing better today, though. So he is not here, and I'm here instead to give you the talk. I'm your substitute speaker. Right, so Angr is a binary, or it's really a reverse engineering tool. And it's a framework that lets you do symbolic analysis of compiled programs. It doesn't do symbolic analysis on the source code. There are other programs that can do that. There's one that operates on like LLVM, intermediate representation. I don't remember what it's called, but you can probably find it if you need that. And the key aspect of symbolic execution is that it can analyze code flow without actually running the code. As you can imagine, this is not very efficient, and Angr is not very efficient, but it's faster than a human in some cases. Humans are really slow at emulating code. Computers are only slow at emulating code. So Angr can do some really cool things. Basically, you can tell it, I want to have these variable states. And Angr will figure out what input you have to give the program in order to get to those variable states. But you're not limited to just variables. You can also say, what does it output? What input do I need to give a certain output state? And you can also use register state. You can say, what input do I need to set RIP to whatever I want? RIP is the instruction pointer, if you didn't know that. So if your program has a vulnerability that's not too hard to find, and you run Angr on it, and you just tell Angr, figure out how to set the instruction pointer to whatever I want, Angr will come up with an input that does that, which can be very entertaining. In fact, you don't have to. It can do more than just find out what you need to control it. It can find out what you need to set it to an arbitrary value. So if you know the address of the getFlight function, you can just put it in Angr and be like, how do I get the getFlight function? I think most of our basic binary exploitation challenges are solvable in this way. So what Angr does is it splits the code into a concept called basic blocks. And what a basic block is it's a section of code that doesn't have any control flow in it. No jumps, no return, not returns or jumps, none of that. And then basically you can generate a control flow graph. You may have seen control flow graphs in other reverse engineering tools like Ghidra or Radare/Cutter /Risen/ whatever they named it now. Anyway, technically, not all edges are jumps, by the way, because not taking a jump is also an edge. Not taking a jump is a decision that you have to make, and so that separates it into a separate basic block. Angr is going to generate a snapshot of the program for every edge that it encounters. And this is called a state in Angr. States contain the entire state of the program. That includes memory, it includes registers, it includes what it has printed out and what it has received as input. And it makes a big tree of states. As you can imagine, the states have a lot of memory. It doesn't store every state entirely, like it's deduplicated. So if you have one state that has just a register change from previous state, and you're just going to store that in a smart way, it's not going to store the whole state again, which is good, because otherwise you would run out of memory. You still might run out of memory. There's one single initial state, which is you have run main. Actually, it's probably you run libc start main, because after that it starts looking at the arguments that you pass to the program, and you can with Angr analyze the impact of arguments. Then Angr has a function called step that will find more states from the current state. What step does is it goes to the next basic block and it runs the symbolic execution engine over it. If the basic block doesn't do anything, or doesn't do anything interesting, like it just multiplies the register by 2 or something, then all it will do is store that change in state to that register. If it's not predictable, for example, if it jumps or if it receives input, or if it does something with input, then Angr will generate more states. If it does things like call libc function or branch based on unknown data, that'll happen. By the way, Angr stubs out libc functions for optimization purposes. You don't need to do symbolic execution on libc functions because you're not reverse engineering them. You have the source code. You know what they do. So what Angr will do is it has Python code, because Angr is written in Python. That's also a reason why it's slow. It has Python code that will come up with the constraints that a libc function applies to the input on the transformation that it does before printing it out. And you can write more of these stub functions yourself. So you can take a hybrid approach where you're reverse engineering the binary at the same time, manually, at the same time as you're running Angr on it. If you find a function that does like a CRC32 or something, that's a classical example of what would make Angr run out of memory. You can write constraints for Angr based on your analysis of that function. Then Angr can use those assumptions to analyze the program faster. Naturally, if you get them wrong, it will break. And it will break subtly and in a way that's very difficult to understand, so be careful. So here's an example of going going between states. You've got some return value in RAX, and you compare it with 40, and you jump if it's less than or equal to 40 to a label. Angr doesn't know what's in RAX. Presumably it came from a function call to someplace, and that's presumably based on user input at some point. So what Angr is going to do is it's going to say, this can reach 2 new states, and it's going to add them to the tree. Each state knows the conditions that led to it being run. That's kind of the whole point. That's how Angr can figure out what input leads to state. And it uses the Python interface to Z3 to combine all the conditions that it knows about at once, and then it can run analysis on those conditions to find ways to get to something you're looking for, or to eliminate blocks that can never be reached under the circumstances that it's analyzing. Z3 is a library which has Python bindings. It's written by Microsoft, actually, I believe. And it's a SAT solver, which basically means it can solve arbitrary collections of constraints. So Angr will generate Z3 constraints from the code flow, and then it'll run Z3 on it, which does all the heavy lifting to find out how to get to that state. Because it runs Z3 on it, it can simplify complex conditions. It can take, like, for example, it can take if A and B and not A and C, and it can say, oh, this just can't happen. And it can also use this to, I don't know what the eval function is, Tristan would, but you can pick an arbitrary state, because you're using Z3 from Python. You can interact with it programmatically. You can pick an arbitrary state and ask Angr to tell you about that state specifically. You can run step more than once until you reach a useful state, and then look at the conditions for how to reach the state. You don't have to do this deep level of integration with Angr, because Angr has some convenient functions for you that will do it for you. The main function is explore. Or no, it's not the main one, but one of them is explore. You give explore an address, and you tell it, how do I get to this address? An address being an address in the program. You say, how do I execute this code? So if you have the address of getFlied, you say, how do I execute getFlied? And Angr can look for it. you can also give it addresses to avoid. So like if somebody decides to be a jerk and put like just call CRC32 in a loop or something just to break your anger. If you can identify those, because people will do that. We do it on we do it at UT, or we do it for UTCTF. We try to make sure people's anger breaks if they try to run it on that program. If you know that an address will never get to where you're going, then you can just tell Angr to avoid it entirely. I mentioned earlier that you can also give Angr stub functions, and so if you can't avoid an Angr trap, which is what this is called, then you will have to stub it out, which should be some work. Angr uses a thing called clarify to create symbolic bit vectors. A symbolic bit vector is just a normal bit vector, but you can use it with Z3. That's just a collection of true or false conditions. I don't know what clarify is. I meant to look it up before the talk. I'm sorry. But anyway, this is just what you use to represent the user-controlled data. So, for example, if you know that the input is UT flagged and has like, I don't know, 19 characters in the flag, then you'll need 8 times whatever that is bits in order to represent the user data. Angr keeps states in a collection of buckets that are called stashes. Huck called them buckets. I guess they're just stashes. But anyway, each stash contains a set of states. The active stash is a stash that contains states that Angr is currently running in parallel and looking for things in them. Well, in parallel, you know, Python doesn't actually have true parallelism, etc. Anyway, dead-end states are states that are broken. Like if you jump to a null pointer, or if you call exit like a good programmer, or you know if you call abort through a failed assertion or something, that state goes into dead end, and Angr will no longer evaluate that state, but it'll keep it around in case you want to look at it later. There's an unconstrained state. If Angr finds one of these states, your program is vulnerable, because this means that it doesn't actually it's not reasonable to ask Angr to continue evaluating this condition because it can do anything, because you control the instruction pointer. But if this does happen, then the program that was being analyzed has a security vulnerability, or you messed up a stub function. You gotta be careful with those. Finally, there'll be a set of found states, which are states that reach what you were looking for. These are the ones you're most likely to want to look for. Obviously, you can get from any unconstrained state to any found state. So if there is an unconstrained state, you should pay attention to that as well. It's probably good practice to always print those out at the hitsist, because those are scary. All right, we have an example problem. By the way, this talk is mainly theoretical. We don't show any actual code in the talk, but you can look on Forever CTF at the Angr tool challenge to get more information on how to use Angr specifically. And there's also documentation on the web. I have the annotated solution to the Forever CTF problem if you want to look at it. I'll be able to sort of kind of explain it. But yeah. That is the end of this spoken portion of the talk. How do I, oh. I can't get out. Oh, wait, here we go. Oh, dang it, it's in full screen. Okay. Huh?
This is why you use Windows.
I've had full screen changed on Windows too. Oh yeah, let me stop recording.